Okay. Well, let's go and get rolling for today. So, announcements. So remember, your quiz is due tonight. Quiz 11 is going to be due tonight, so make sure you get that done. We've covered all the material for that. So quiz 12, right now it's scheduled to be due on Friday. Probably going to wait till Monday on that one. I haven't yet delayed that, but I think that we will. The problem set that I posted on Friday is going to still be due on Friday. We'll have covered the material by then. And then finally, group work, as I said, it would be either Wednesday or Friday this week. We're going to go ahead and have that on Wednesday. So I think that I'll get through the material, enough material today for you guys to do the group work effectively. So on Wednesday, come ready to do your final group work assignment of the semester, okay? So of course, we're down to the last 2 weeks of the semester at this point in time, okay? All right, so our riddle, this one's really dumb. What tree is most warmly clad? The fir tree, exactly. Isn't that? It's so stupid. Anyway, I had to do it. I'm sorry. I can't help myself. Okay, so on Friday we left off right here. So I'm going to be kind of stuck behind here. My wireless system's not working again. But on Friday we left off essentially here, just looking at the nomenclature that's currently used and by convention to name fatty acids, this 18:1 delta 9. So we went over that and had also introduced the idea of beta oxidation. The most important aspects of this slide, well, there are a number of them, but certainly the most important aspect as we go into this next portion of this is going to be that third carbon is going to be called our beta carbon. Okay, so the pathway that we're about to go over is called beta oxidation. So when we think about that name, what we're thinking about is how that carbon there that I just pointed to, that third carbon on a fatty acid, is going to be oxidized. And it's going to go through these successive rounds to oxidize essentially completely and break up a fatty acid completely into 2 carbon units of acetyl-CoA. Okay, so that's what we're going to be thinking about today. We'll start off today looking here at the oxidation of a saturated fatty acid, palmitoyl-CoA. Palmitoyl-CoA, just so you all know, is this fatty acid, 16-0. Okay, it's fully saturated, does not have any double bonds, and it has 16 carbons. Okay, a fairly common fatty acid in a mammalian system, because when you make fatty acids, that's the end product of the central portion of the fatty acid synthesis pathway. Okay, so it's fairly common fatty acid. Okay. Now again, putting us into the larger context of the things that we've talked about, remember what has happened to get this fatty acid to this point. We have seen that fatty acid potentially ingested within your diet. It was packaged into chylomicron and triglycerides. It then maybe potentially made it into a cell right out of the chylomicron, or potentially had to go all the way to the liver, be repackaged in a VLDL, and then make it to the tissue. Once in the tissue, it would be converted to acyl-CoA. From that acyl-CoA, it would be converted to acyl-carnitine so that it could be moved in the mitochondria and then converted back to an acyl-CoA. So all of those steps have taken place up to this point in time, and now we're ready to look at here how the body is going to then break down a fatty acid for energy purposes. Okay, and it's actually a fairly straightforward pathway, especially when we're looking at a saturated fatty acid. Okay, it consists of essentially a dehydrogenation reaction. That would be our first step. A hydration reaction, that would be our second step. Another dehydrogenation reaction, our third step. And then finally what would be considered a thiolysis step, or if you want a transacetylation step. Okay, so those are our 4 steps. 2 of them reductive, 1 of them a hydration, and then finally the last one is just really a cleavage step. Okay, so if you can just keep that in your mind, right? Redox, hydration, redox, cleavage, then it can break down this pathway into some fairly simple things. Okay, so what you are looking at here then would be that first step. There's going to be 4 of them, as I've kind of outlined for us, and the first step is going to be catalyzed by a dehydrogenase, again redox step, Acyl-CoA, a very general name. Acyl-CoA dehydrogenase is the name of the enzyme that does this. There are actually several different isoforms in a cell depending on the length of the fatty acid chain. Okay, so if it's real long, then there's one acyl-CoA dehydrogenase that will work with that. And as they get shorter and shorter, there'll be different quote-unquote acyl dehydrogenases that carry out the same reaction, but they have different specificities for the length of the carbon chain. Okay, but in any case, acyl-CoA dehydrogenase is simply going to do this. It's going to introduce a double bond, a trans double bond. So that what you're left with is trans delta 2 enoyl CoA. Okay, that's the general name of the product of acyl-CoA dehydrogenase. Okay. Now, this reaction requires FAD. FAD, flavin adenine dinucleotide, okay, and that will make FADH2. Now, just a point of interest, you don't have to necessarily write this down, but if you want to have something fairly easy to remember in terms of what produces FADH2 and what produces NADH, generally speaking, when you're taking an alkane, single bonds, and making an alkene, a double bond, FAD is used because it's a stronger oxidizing agent than NAD+. NAD+ is typically used to go from an alcohol to a ketone or an aldehyde. Okay, so just so you have that in your mind. Okay, you can go back even look at the citric acid cycle, and that holds true in the citric acid cycle. Okay. Now, that FADH2, okay, I'm going to bring this over here and look at this over here. We have talked about in lecture 9, we looked at how complex 1 and complex 2 lead to the production of QH2. We looked also, when we were looking at carbohydrate metabolism, how the glycerol 3-phosphate shuttle will lead to FAD and QH2. Okay. We are now at the point where we're at fatty acid breakdown, and we are looking at this enzyme right here, acyl-CoA dehydrogenase. That whole enzyme is here. The reaction that's shown here is that reaction that we just looked at over on our left. That FAD, like other FADs in the cell, doesn't actually leave the enzyme, okay, just like it didn't for complex 2, succinate dehydrogenase. That enzyme will have to take that FAD, reduce FADH2, to essentially the electron transport chain, and that's what you're looking at in these series of arrows. Okay, this enzyme is called ETF, and it will take electrons from acyl-CoA dehydrogenase. If you're really, really curious, ETF stands for electron transferring flavoprotein. Okay, so it's just going to take, has a flavin nucleotide in it. It's going to take electrons from acyl-CoA dehydrogenase, and it's going to transfer those to another enzyme, this guy right here, that's called ETF-Q oxidoreductase, which is going to take electrons from ETF and pass them on to Q, making QH2. So if you go back and look at chapter 9, there was a slide in chapter 9 right before getting to complex 3 where I showed you all the sources of electrons that could come and make QH2. Okay, and I mentioned fatty acids. They said, well, fatty acids will do this as well. Okay, well, here is the completion of that slide, essentially. Okay, it starts at this acyl-CoA dehydrogenase. All right. That's it in terms of the first step of the oxidation of a saturated fatty acid or palmitoyl-CoA. Okay? And we've got this now trans double bond that has to be dealt with. Questions on that? Okay. All right, so let's go ahead and move to our second step. So that's a redox step. Like I said, the next step will be a hydration step. Not a lot to say here. It is going to hydrate this. Okay, double bond. It's going to add water to it. You need a hydratase to do this. Enoyl-CoA is our hydratase. Enoyl-CoA is the general name for this. But enoyl-CoA hydratase is going to add, okay, that hydroxyl group you see here to the beta carbon. Remember, this is our beta carbon. Okay, our third carbon. And in our last step, we had a double bond produced between our alpha and beta carbon. That double bond is removed in the favor of putting a hydroxyl group on the beta carbon. Okay? The beta carbon is being reduced, or I'm sorry, not reduced, but oxidized in this case. Okay? Now that leads to this product, beta hydroxy acyl-CoA. Okay? Meaning that there is a hydroxyl group on the beta carbon of the acyl chain. Okay, that's our naming convention. And it happens to be in the L isomer. Now, the next step, so that's step 2. The next step then is another redox step. And you see here, NAD plus is used. Okay. As I mentioned when I was talking about FAD, FAD is alkane to alkene transitions, NAD plus alcohol to ketone transitions, and that's what we see here. Okay, NADH accepts the electrons, or NAD plus accepts the electrons, and we now have on our beta carbon, okay, a ketone. Okay, and that carbon is much more reduced, much more oxidized than it was at the beginning of our process. Okay. The enzyme name that does this, beta hydroxy acyl-CoA dehydrogenase. Essentially, it's substrate's name dehydrogenase. This then can go on to the electron transport chain, specifically complex 1. Okay, and of course that will make a number of ATP depending on the size of the C ring in the ATP synthase molecule. And what you're finally left with, we're on step 3 now. What you're finally left with is this beta keto acyl-CoA. Okay. Again, beta, it's got a keto group on the beta carbon, acyl-CoA. Right. And if you pay attention, right, I mean, this is where your organic chemistry can become helpful, right? If you pay attention to these names and just kind of look at the structure of the molecule, right, I mean, it starts to hopefully it makes sense to you in terms of how these names are being put out there, okay? And then, like I said, the last step is cleavage, okay? What would be called the cleavage step. The enzyme goes by really 2 different names. Acyl-CoA acetyltransferase is one of the names, and that tells you a little bit more what it does. It transfers an acetyl group to coenzyme A, okay? Thiolase is another name that it goes by, okay, because it is going to essentially break the bond between the acyl chain and this acetyl group, okay, using thiol chemistry. But what you're left with at the end of this is acetyl-CoA, and in this case, a C14. Okay, so now we've got this guy here, and this would be 14 colon 00. Okay. That will be after round 1. Okay. And now it's going to start back again at step 1, redox, hydration, redox, cleavage. And then it'll go to the next round, right? And you get the idea, and it just keeps doing this over and over and over again. At the end of it, it's always an acetyl-CoA that's made, and then you could just essentially say it would be CN-2, where N would be the number of carbons that round started with. And they're always removing 2. Okay? Now, of course, this acetyl-CoA, this can enter the citric acid cycle, and that can then, in the citric acid cycle, lead to the production of 3 NADH, 1 FADH2, and 1 ATP equivalent, GTP or ATP. Okay. Yeah, question?
Do you ever have an odd-numbered fatty acid?
Yep, we're going to look at that. Yeah, so the question is, can you ever have an odd-numbered amino acid? And you can. They're rare. You generally don't find them in your diet, although they can exist, just because there's not a lot of organisms that make them. Okay, but you do find them. You can ingest them. You and I don't have the capacity to make an odd-numbered fatty acid. So certain plants do, though. And we'll also talk about unsaturated fatty acids here in a little bit. All right, now, here's what I want to do. I want to go ahead and ask you a question. So that's our oh, crud. That's not good. Okay, I want to ask you this question. I'm going to go ahead and read the question, and you guys can talk amongst yourself. Let's do this. Does it show up on yours? It says I'm disconnected. Can you guys get it? Oh, you can. Awesome. Okay, good. Okay, so let me pause it for a little bit. But if palmitoyl-CoA, so that's our 16-0 fatty acid, if that's completely broken down into 2 carbon acetyl-CoA units, how many rounds of beta oxidation would this require? And how many FADH2 and NADH will be produced? Okay, so text me your answer with 3 numbers. Number of rounds, number of FADH2s, and number of NADH. What do you think? Okay, and you don't need to, you can just do it in that order, right? So round, FADH2, and NADH, you don't need to have any text with it, okay? All right, so I'll give you a minute, 39 seconds to answer that question. Talk to your neighbor about it. What do you think? How many rounds is that going to take in NADH and FADH2? On your marks, get set, go. Okay? Maybe go. There we go. You don't have to, no. You don't have to include the NADH or FADH2 from the citric acid cycle. You can if you want to. Okay, about 15 seconds left, so submit something if you haven't done so already. Okay, about 5 seconds left. Okay, let's check this out, see what people are saying here. Okay, so I've got 7:14:7, 8:24, 8:9. What just happened? Why did I do that? Show results. There we go. Okay. All right, so 7, 7. Okay, you can stop doing that. Okay, 7, 7, 7, 7, 7, 7, 13, 27. Okay, 6, 1, 6. All right, so 7, 8, 8. All right, so I got answers all over the board, all over the place. Okay, so I'm going to highlight this one. Okay, so 7, 8, 8 will be the correct response for this. Okay, so let me go ahead and show you this. Okay, when we look over here, let's do this. Okay, this is a figure that your book uses. I'm going to go ahead and add a little bit something to it. Actually, let me do this like this. There we go. Boy, I had a hard time drawing that loop. I was confused, like, okay, all right, there we go. So we'll do this. They didn't include this on this, but we'll go C16 here, okay, and that's an acetyl-CoA. So each one of those little loops on this diagram is one of those rounds that we just talked about, all 4 steps, right? Redox, hydration, redox, cleavage, okay? So there's 1, 2, and every time you're doing this, you're removing 2 carbons from the 16 carbon molecules. So 3, 4, 5, 6, and then at the last round you get a C4, okay? Not an explosive, you just get a carbon 4 based compound, okay? So And that then only takes one round to split it into two. So there's only going to be a total of 7 rounds. Okay. Now, in that process then, and actually I'm trying to think here. No, it wouldn't be 8-8. It would be 7-7-7. Because because you have the last round only produces an NADH and one NADH and one FADH2. You had 8 acetyl-CoA. So I was wrong. Okay, give myself a red check minus. I didn't think about it. I was worried whether you guys were getting your answers in, and I was thinking about that instead of what the actual answer was. So it's going to be 7-7-7, not 7-8-8-8. Okay. So 7 rounds. Each round produces an NADH, and each round produces an FADH2. Okay. I'm sorry. Right. So it will have a total of 8 acetyl-CoAs though. Okay, and then those 8 acetyl-CoAs can go on and make, it would be 24 NADH, 8 FADH2s, and 8 ATP in the citric acid cycles. Okay? Right. And that will be for, of course, a 16 carbon fatty acid. Okay. Any questions on that? Sorry, I screwed you up on that one. Yeah, in the back. 7. Yeah, so it would be 7 total. So it would be 7 rounds, 7 NADH, 7 FADH2. And then I didn't ask this in the question, but it would be 8 acetyl-CoAs. Okay. The number of rounds in the case of a saturated fatty acid will always equal the number of NADH and FADH produced. Okay. Acetyl-CoA, the amount of acetyl-CoAs will always be 1 more than the number of rounds it takes. Again, in a saturated fatty acid. Yep. Other questions? Okay, let's do this. Let's talk about an unsaturated fatty acid, and there's 2 different portions of this slide. We'll talk about everything on your left to begin with, okay? So let's talk about what's on the left, and in this, we're going to do this fatty acid, oleuil-CoA, and that is this, is 18 colon 1 delta 9. Okay. 1, and this would be cis. Okay, so 1 cis double bond at the 9th carbon. Okay. When there is unsaturation, there has to be the invocation of different enzymes when that double bond is encountered in the beta oxidation process. Okay, so let me go ahead and focus in on this over here. Okay, and what you see here is this. The first 3 rounds of beta oxidation or cycles of beta oxidation will be identical to what we just talked about. Okay, redox hydration, redox cleavage. And that will make then 3 acetyl-CoAs. And it will make the NADH and FADH2s as well. Now what you're left with, because you're cutting here, 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 what you're left with is something at the end of that 3rd round, and this is the start of the 4th round. Okay, so I'll put that start of 4th round. You're left with this product that is not a substrate for acyl-CoA dehydrogenase. Okay, so this is not a substrate. Oops. Straight for acyl-CoA dehydrogenase. And you say to yourself, we've talked about a lot of dehydrogenases today already. Which one is that? That's step 1 of beta oxidation. So acyl-CoA dehydrogenase is the one that produces the FADH2, the very first step of and it will produce If you remember, it will produce that trans double bond. Well, there's already a double bond at the beta carbon. Right? So the acyl-CoA dehydrogenase can't do anything with that double bond. It can't introduce a new one. So this actually has to then undergo an isomerization reaction. Okay? And so there's this new enzyme, an isomerase, enoyl-CoA isomerase, that moves this double bond to here. Okay? And this now, by the way, if you're looking, this is your beta carbon. This was your beta carbon before. Okay? So it just moved it over between the second and third carbon. It was between the third and fourth carbon. Okay? So it's hard to keep these things straight. This is number 3 carbon here. This is number 4 here. And now we've got number 3 here and number 2 here. The name of this actually tells you a little bit about that. It's the delta 3 to delta 2 enoyl-CoA isomerase. It'll move the double bond from the third carbon to the second carbon. Okay. That then is a substrate for the hydratase. Some of you are just dying for a Hydra joke. I just know it. Okay. And I just supplied it. There you go. There's your Hydra joke. Hail Hydra. Okay. Anyway, hydratase, that's the substrate for hydratase, so that will then begin that fourth round. Okay, so now you're back on it. You skip the dehydrogenation, the redox reaction. You go to an isomerization reaction in the fourth round of this. From the isomerization reaction, you go to hydration, and now you are back in the cycle of redox cleavage. And then the rest of the rounds will be the same, okay, after that, because you've effectively removed the double bond, okay? And there will be several cycles after that, okay? Right. So let's see if you followed that. Let me ask you another question, okay? So that was oleoyl-CoA. Remember, oleoyl-CoA is 18:1 delta 9. Okay? So I'm going to ask you the same question. How many rounds, how many FADH2s, and how many NADH are you going to produce from this? I'll actually legitimately think about the answer while you guys are doing it, okay? All right. I will give you a minute 45 or minute 40 only. Well, think about it for a little bit. I'll give you a minute 40, okay? On your marks, get set, go. What do you think? Okay? What do you think? How many rounds? How many FADH2s? How many NADH2s are you going to get? Okay? Are you guys able to answer? Are you good? No? No, that's because it's locked. How about now? Good? No across the board? How about now? My timer's not even working. What's that?
I really like the last question.
How about now?
There you go.
I got some funky Wi-Fi going on up here. It's funky in my space. I don't know what about your space, but mine is bad. All right. It would be part of one of the rounds. Yes, the isomerase? Yep. Okay, I'm paused at 28 seconds, so I don't know what the deal is, but I'll give you probably less than 28 seconds. I'll give you 15 more seconds. How about that? 15 more seconds. Five more seconds. Okay. I'm going to go ahead and stop it. I don't know. I'm having a very unresponsive system here. Okay, so, okay. Yeah, that looks about right. So let's go ahead and show these results. Okay, so we got a bunch of 8s, 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 888, 888, 878. Okay, oh, that's okay. I just want to look through this. Okay, so I'm going to highlight this one here, 878. So that will be the correct response on this one. Okay, so if you go, let's go ahead and come back here. Let's think about this. So because it's an 18 carbon molecule, right? 18 divided by 2 is 9. I think all of you know that. Okay, the number of rounds is always going to be your total number of carbons divided by 2 minus 1. If you can keep that in your mind. Okay, so 18 divided by 2 is 9, minus 1 is 8. So the number of rounds is 8. The number of FADH2s that's going to be produced in this is going to be 7, though. And the reason is because our fourth round doesn't produce an FADH2. So the fourth round is the one that we kind of highlighted here. Okay? Not a substrate for acyl-CoA dehydrogenase, which means it's skipped FADH2 production in that fourth round. Because it skipped right, it went right to the isomerase, and then from the isomerase to the hydration. Okay. And then it went from the hydration to the next dehydrogenase. Okay, when that dehydrogenase makes NADH, so the number of NADH would be the same as what you'd expect. It would be 8. Okay, same as the number of rounds. All right, so you lose, in this case, you lose one FADH2 because, again, in this case, when you think about an unsaturated fatty acid, it's in a more oxidized state to begin with. Okay, and so you expect then less electrons to be able to come off of it, so you expect then hopefully less reduced coenzymes to be made. Okay, so 878 is the number. Now it would be 9 total acetyl-CoAs. Okay. All right, questions on that? Yeah.
So just to recap then to make sure I got this. So then on that fourth step then, so that acetyl-CoA dehydrogenase doesn't work on it, and then the benzoyl-CoA isomerase comes in, pops that set off, and then it keeps on working with the acetyl-CoA dehydrogenase again?
That's right.
Okay.
Yeah, you got it right. So if you didn't hear what he said, is that come that fourth round, because we've got this double bond in the wrong place, all right? This is the issue right there. That double bond's in the wrong place. The first dehydrogenation reaction of the beta oxidation is going to put a trans double bond between the second and third carbon. Well, right now there's a cis double bond between the third and fourth carbon. So that dehydrogenation reaction can't put that double bond there. Otherwise, it'd make a carbon with 5 bonds around it, right? It can't do that. All right, so it then has to go to this isomerase that will then move, that will actually make the trans double bond that the dehydrogenase normally would. It just moves it over, okay? And then you pick up right back where it left off of the hydration instead of the dehydrogenase. Okay. Yeah?
What if you end up with a double bond, like one carbon over, so then you can't just move it from cis to trans?
Okay, so the question is, yeah, so what if you have a cis 2,3 double bond, okay? I don't think you could metabolize it. Okay, I think the metabolism would stop right there. There's not an enzyme, I don't believe, and this is, in my, lack of omniscience, I don't believe that there's an enzyme that could isomerize that to a trans double bond. I could be very wrong. Here's the thing, generally speaking, you do not find double bonds that begin in that fashion that you would have them, that you'd have it when it's going through beta oxidation, that you'd have it appear on the second carbon to begin with. Okay, usually it's down further. Okay. Okay. I could be very wrong in that, but that's my suspicion. Other questions? Okay, let's complicate it. Why not? Some of you say, oh yes, that's what you need in biochemistry. That sentence scared you right there. Let's complicate it. Okay, well, let's do it anyway. I'm going to do it anyway because it has to be done. So now what we're going to do is look at this linylyl-CoA, which is essentially the same fatty acid that we looked at except for an additional double bond. 18:2 delta 9:12. Okay. Now we've got a double bond starting at the 9th carbon and the 12th carbon. We've already dealt with really what happens with the 9th carbon. Okay, we dealt with it over here. Okay, so that's going to happen as we've already discussed it. You get, okay, and I'll try and use the same coloring scheme. We talked about the 3 acetyl-CoAs, 3 rounds of beta oxidation. Okay, let me go ahead and zoom out here a little bit. So 3 cycles. Okay, we then get the isomerase. We used the pink color for the isomerase in the last one. And you get this isomerase here is the isomerase here. Okay, same thing that would happen in our prior discussion. Okay, we've got a cis double bond between the 3rd and the 4th carbon, so we have to have an isomerase to put it between the 2nd and the 3rd carbon, and then you go on hydration, dehydrogenation, cleavage. Okay, now here's the issue with that. So all of this right here, all of that is seen entirely over here. Okay, especially that top half. Okay, there we go. Okay, awesome. It worked. We got back. Let me actually do it like this. It's really more of this. Okay, everything that we talked about there is the same. Okay, I mean, nothing different. Now here's the next thing, okay, and this is where it becomes complicated. Okay, go ahead and focus in here. They say in this slide, and I wish they put it in this slide, but they didn't. After that cleavage step, after they dealt with the carbon or the double bond and what would have been the 9th carbon, they then go on to say, okay, you've got that cleavage step after the 4th round, so this would be the 4th round here. Okay, and you've got the 3 rounds preceding it. So up here would be the first 3 rounds. So now we're on the 5th round. And the 5th round is a little bit strange. We need more enzymes, okay? The 5th round starts like any other round in beta oxidation. It starts with acyl-CoA dehydrogenase. They even say it, first oxidation of 2nd cycle. So this would be acyl-CoA dehydrogenase. Which is the first step in beta oxidation, a round of beta oxidation. So this will make, just for reference for you, makes FADH2. Okay. But it also, because we have this other double bond to deal with. Okay, so there's that original double bond and what would have been called the 12th carbon. Okay. To start off with, that double bond I just circled is this guy right here. Okay, that's translated all the way down here. Now it's on the 4th carbon because we've been removing carbons all along. The dehydrogenase step makes our trans double bond, right? So this was acyl-CoA dehydrogenase made this double bond, the trans one. Now that right there, what you're looking at, it's called trans delta 2 cis delta 4. All right, and then you can call it whatever number of carbons you have on it. But trans delta 2 cis delta 4. This is not a substrate. For hydratase. Of course, I can't put the whole word hydratase there, for hydratase. Okay, so we can't then go from dehydrogenation, hydration, we have to do something else. Okay, and so what it does is this, it's really kind of strange. It's going to combine the two double bonds into one double bond. So there's actually going to be a reduction step, and then we're going to do an isomerization step. So these two double bonds here and here, the one between 2 and 3 and 4 and 5, are going to be combined into one by this reductase. Okay? And it's between now the 3rd and the 4th carbon. So we can just say this combines delta 2, and delta 4 double bonds into 1. Okay? And that one is sitting right here now. This guy right here is the trans delta 3. Now, here's the fun part about this. It uses an NADPH to do this. Okay? So it has to, because it's a reductase, it has to get electrons from somewhere, and it's going to take those electrons from an NADPH molecule. That NADPH molecule, in accounting terms, okay, is essentially an NADH equivalent. And so when we start to look through this, and you start to consider, okay, well, how many NADH, how many FADH2s do we make in this process? We have to subtract an NADH from our process because we use one to do the reductase. Okay, so in our 5th round, we have to subtract one NADH. Okay. Now there's an isomerization reaction after that. Isomerization just simply moves. Okay, so moving on to this now, enolylcoase isomerase is just going to move that double bond from 3 to 4 to 2 to 3. Okay, so it just moves it to here. That is a substrate for the hydratase. It will hydrate, it will dehydrogenate, it will cleave, and then it will go on, and it will go on for the rest of them. Okay? So, like I said, it becomes a little bit complicated in this, right? Because you have to, essentially in this process, you are minus 1 FADH2 and you're minus 1 NADH. Okay? The minus 1 FADH2 is because you skip the acyl dehydrogenase in the 4th round. You're minus 1 NADH because you have to use an NADPH, okay, with the reductase reaction, combining 2 double bonds into 1. Okay? Yes?
If the double bonds weren't directly next to each other, so if it was like delta 9, 15, would you just use the process on the left twice?
Yep. Yeah, so the question is, what if it was delta 9, delta 15? Would you just use the process on the left? Yes. So then you would just do 2 rounds of that. Yes?
So with that NADPH being equivalent to an NADH, why doesn't it just use an NADH or NADH?
The answer is because. Yeah. I don't know. The question, if you didn't hear him, if that NADPH is equivalent, and this is an accounting terms, to an NADPH, why not just use the NADH, right? So NADH and NADPH, they're only a phosphate group different, right, on a ribose ring in it, okay? They are used, though, however, in very different ways in the cell, okay? We've even kind of seen some of that. NADPH is typically used in biosynthetic pathways. It's also used in oxidative stress pathways, okay? Whereas NADH is typically used in catabolism. The question why is one that's hard to answer, right? I mean, it has to do, of course, with the specificity of the enzymes for NADH and NADPH. But then the really bothersome question is, why did those enzymes develop a higher specificity for NADPH versus NADH? And that answer is because. I don't know if we know the answer to that question. So, other questions? No? Okay, I'm going to move on. So I do want to do this real quickly, okay? We've covered enough material for the group work on Wednesday, so we'll definitely do the group work on Wednesday. Yes, question?
Can I just ask this question on it? What is the rounds FADH2 and ADH for that one?
Oh, so what are the rounds? Okay, so the rounds on this one, so but I'm not going to ask that question. But if you were to look at this, the number of rounds would still be 8. Number of acetyl-CoAs would still be 9. The number of FADH2s would be 7, and the number of NADH would be 7 as well. Okay, because you subtract 1 NADH from the whole process. Okay? All right. Now, let's do odd chain. So odd chain fatty acids are rare but important. Okay? And there was a question earlier on this. So let's say that you have an odd chain, a 17 carbon fatty acid or something like that. Again, they're pretty rare, but let's say that you have them. You will get to essentially the last round of beta oxidation, and you will have a fatty acid that is 5:0. All right, 5:0 will break down into acetyl-CoA. In the last round, the cleavage step will lead to acetyl-CoA and something called propanyl-CoA. Propanyl-CoA, you'll notice, has 3 carbons. Okay. Incidentally, isoleucine, valine, and methionine, when you start to oxidize those amino acids, they will also produce in their end propanyl-CoA. All right, so we're kind of killing 2 birds with 1 stone. This would be the end of those 3 amino acids catabolism as well as odd chain fatty acid catabolism. I don't want to spend an inordinate amount of time on this, but I do think it's important to go ahead and show this. Okay, so I will just quickly move through this. The first step in dealing with propanyl-CoA in terms of oxidizing it is to carboxylate it. Okay, and propanyl-CoA carboxylase is the name of the enzyme that would do this, and it makes this 4-carbon molecule here. Biotin's used, and it's an ATP-dependent process. If you go back to our discussion that when I first introduced pyruvate carboxylase, they said, oh, there's these other carboxylases in the cell. They all use biotin usually, and they're all ATP-dependent. Okay, so this has got almost an identical mechanism to pyruvate carboxylase. Okay, it makes the products is methylmalonyl-CoA. Okay, now methylmalonyl-CoA. This guy here, this is our 4-carbon molecule. And again, I don't want to spend a lot of time on this, okay? It'll go through an epimerase reaction and then a mutase reaction. Essentially, it's just going to move the carbons around, okay? And you can look at this and study this on your own time if you really want to. But the epimerase is going to go from a D, okay, methylmalonyl-CoA to an L-methylmalonyl-CoA. Okay, so it just changes the stereoisomer of one of the carbons. The mutase will swap the coenzyme A group to a different carbon, and what you are left with is this, succinyl-CoA. Now, you should say, oh, yeah, succinyl-CoA, that's a citric acid cycle intermediate. Exactly, okay? Succinyl-CoA is the product of alpha-ketoglutarate dehydrogenase complex, okay? It is also the product of this process as well. So this can feed into the citric acid cycle. Now, here's what's really interesting about this. I have said, and I'm going to stick to this, right? Fatty acids do not make glucose, cannot lead to glucose production, except for an odd chain fatty acid. And the reason is because an odd chain fatty acid at the end can feed into the citric acid cycle at succinyl-CoA, which can then lead to net accumulation of oxoacetate. Net accumulation of oxoacetate can lead to the net production of glucose. Right, so strangely, odd chain fatty acids can make glucose. Okay. Not a ton of it, but it can make it. Okay, all right. So we'll stop there. We'll pick up on regulation on Friday. So come prepared to do your group work on Wednesday. What's that? It would make it anaplerotic, right? Yep. So that would be an anaplerotic process. Right. And for every 1 odd chain fatty acid, you can get 1 glucose out. Actually, you'd have to have 2 odd chain fatty acids to get 1 glucose.